Next, we are going to discuss the psi of Astornis, a very important property of primes. But before going into details, we will discuss another important result related to primes. That is, that given number is a prime. For smaller numbers, we can easily say that 3, 5, 7, 11, they are primes. What about bigger numbers like we have 509, 701? How can we say this is prime or not? So it is not that easy, but by method, by steps, proper steps, we can easily see the given number is prime or not. So for this, we need property of composite number, that if an integer a is strictly greater than 1 is composite, then a may be written as product of two numbers where both b and c are non-trivial divisors of a. Now assuming that b is less than equal to c, so there is no harm in assuming this. You can go other way also, and multiplying by b on both sides less than equal to bc, which is actually a. So we get b is less than equal to under the root a, just taking square root on both sides, because as b is strictly greater than 1, at least one prime factor p of b, p divides b and b divides a, imply p divides a also. So p is also a factor of a. And where p lies? As p divides b, so p lie between, p has to be less than equal to b. And what is b? b is less than equal to square root of a, which imply this prime factor is less than equal to under root of a. So this was the property here. The result is a composite number a will always have a prime divisor p satisfying p less than equal to square root of a. Let's test this for a is equal to 509. So we will take its square root. So clearly it lie between 22 and 23. So we will write down, all primes less than 22. So they are namely 2, 3, 5, 7, 11, 13, 17. Now let's check whether any of the numbers divides 509. So when we divide 509 by 2, we get 254 quotient and 1 remainder. 509 divided by 3, we get 169 quotient, 2 remainder. When we divide 509 by 17, we get 29 quotient and 16 remainder. When we divide 509 by 19, we get 26 quotient and 15 remainder. So we will see none of the primes less than 22 divides 509. Means 509 is prime number. Answer. Determine whether the given integer 701 is prime by testing all primes p as possible divisors. So first we find the square root of 701, which clearly lie between 26 and 27. So let's write all primes less than 26 are. They are 2, 3, 5, 7, 11, 23. So let's check whether any of these primes divide 701. So when we divide 701 by 2, we get 350 quotient and remainder 1. Now we divide 701 by 3. Quotient is 233, remainder is 2. Now divide 701 by 5. Quotient is 140, remainder is 1. Let's divide 701 by 23. Quotient is 30, remainder is 11. So we see none of primes less than equal to root of 107 divides 701, which means 701 is a prime. Answer. Now let's discuss sieve of Astornis. This is a method of finding all the primes below a given integer. So now the steps are, we start by writing down integers from 2 to n in their natural order and then systematically eliminating all the composite numbers by striking out all the multiples of 2p, 3p, 4p, 5p and so on for all primes less than equal to square root of n, and the integers left are gives us the list of all the primes. Let's write down primes between 2 to 30. So for this we will find out p less than equal to square root of 30. Square root of 30 will lie between 5 and 6. So we will write down all the primes less than equal to 5. So they are only 3, 2, 3 and 5. So first we will write all the numbers from 2 to 30 in their natural order. 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 11, 12, 13, 14, 59 and 30. Now we will strike out. First we will strike out multiples of 2, then multiple of 3 and multiple of 5. But take care that we will not strike out 2, 3, 5 because they are already primes. 2, 3 and 5s. Just multiples of 2. So first multiples of 2 are 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28 and 30. So now we will strike out multiples of 3. So they are 9, then 15, then 21, 27. Now we will strike out multiples of 5. Multiples of 5, there is only one number, that is 25. So the numbers we are left with are the required primes. So what they are? 2, 3, 5, 7, 11, 13, 17, 19, 23 and 29. So these are the required primes lie between 2 and 30. So very easily you can find out all primes that lie between 1 and 100. And also there is another question, find all primes lie between 100 and 200. So go through same method, just write numbers in their natural form and then find out. For this we will find out primes less than 100 and here we will write down primes less than 200 and their multiples will be striked out and the numbers left in the list are the primes. That's it. Now we will discuss some problems from 3.2 problem set. Assuming that Pn is the nth prime, establish the following statement greater than equal to 5. So we prove this by induction. So given n is greater than equal to 5, so for case 1, n will start from 5. So we know P5 means fifth prime. And how much is that? Very easily we can write it as 11. Now putting value 5 on the right hand side, and how much is 2n plus 2n minus 1? So 2 5s are 10 minus 1 is 9. So clearly 11 is strictly greater than 9. The result is true for n is equal to 5. Case 2. So let result is true for n is equal to k, means what we are taking, that pk is greater than 2k minus 1. So this we are assuming true. Now in the third part, now we know if pk is the kth prime, then pk plus 1 is even. Therefore, next prime is pk plus 2. So that means pk plus 1, that is k plus 1th prime, has to be greater than equal to pk plus 2. Now putting the value of second result, that pk is strictly greater than 2k minus 1 plus 2, which will comes out 2k plus 1, which may easily be written as 2 times k plus 1 minus 1. So hence the result is true for k plus 1. So by mathematical induction, result is true, hence the answer. Now we prove second result. None of the integers is a perfect square. Let Pn is P1, P2, Pn plus 1 with a given number. Since P1 is the first prime, that is 2, therefore multiple of 2 are, any multiple of 2 is even, which makes P1, P2 up to Pn is even. And when we add 1 to even, it becomes odd. So Pn is odd. Because this is even, plus 1, it makes it odd. Now by division algorithm, every odd integer is of the form, when divided by 4, it is 4k plus 1 and 4k plus 3. So we claim Pn is of the form 4k plus 3 for all n. If possible, let Pn is of the type 4k plus 1. That means P1, P2, Pn plus 1 is 4k plus 1. So 1 1 cancel from both sides. P1, P2 product is equal to 1 1 cancel. This is 4k. Or as P1 is 2, so 2 will cancel from both sides. We have P2, P3 up to Pn as 2k, which is not possible, as all pi's for I strictly greater than 1 are odd. So our supposition is wrong. Pn is of the form 4k plus 3 for all n. Therefore, Pn is not a perfect square, because we know odd perfect square are of the form 4k plus 1. And the third part is the sum 1 upon p1, 1 upon p2, 1 upon pn is never an integer. Let this sum is an integer and say it is a. And let product of p1, p2, pn is capital P. Then multiplying by capital P on both sides, p by p1, p by p2, capital P by pn is equal to pa. Clearly, p1 divides ap, and then p1 will divide p by p2. This is true because capital P is product of p1 to pn, and p by p2 means p2 will divide p2, but it is p1, p3, pn. So it's a multiple of p1, so p1 will divide this. So similarly, p1 will divide p by p3 and so on. p1 will divide p by pn. So which means if p1 divide all these numbers, then p1 will divide their linear combination. So p1 will divide ap minus p by p2, p by p3, p by pn. And when we subtract this from this, we are left with p by p1, which imply p1 divides p by p1, which means p1 divides p2, p3 up to pn, and which further means that p1 has to be equal to pj for j lie between 2 and n. But they are distinct primes, so we get a contradiction. Hence 1 by p1, 1 by p2, 1 by pn is never an integer. Answer. The definition: rep unit. An integer which is a string of ones is called rep unit. For example, R2 is 11, R3 is 111, Rn is n times 1. And very easily we can find that Rn, which is this, may be written as 10 power n minus 1 by 9 for n greater than equal to 1. Now let's try to verify some properties for rep units. For rep units Rn, verify if n divides m, Rn will divide Rm. So given n divides m, so by definition of divisibility, there exists some integer k such that m is equal to nk. And we already seen that how much is Rm? Rm is 10 power m minus 1 by 9. Putting value of m here, this is 10 power nk minus 1 by 9, which may further be written as, now factorizing this 10 power nk as 10 power n power k minus 1 by 9 as 10 power n minus 1 into 10 power n k minus 1, 10 power n k minus 2 up to 1 by 9. Now combining this is Rn. So using again definition of divisibility, that Rm is integral multiple of Rn, which means Rn divides Rn. Answer. For rep unit Rn, verify if D divides N, D divides M, D divides Rn plus M. Now let's write how much is Rm plus N. It is 10 power M plus N minus 1 by 9. So which may further be written as 10 power M plus N, adding 10 power M and subtracting 10 power M. And taking 10 power M common, we have 10 power N minus 1, 10 power M minus 1 by 9. So which is equals to 10 power M Rn plus Rm. Now given D divides Rn and D divides Rm. So D divide their linear combination, 10 power M Rn plus Rn. And what is that? D divides M plus N. Required answer. So by definition of GCD, there exist X and Y belong to Z such that Mx plus Ny equals to 1. Now let D be the GCD of Rm and Rn. So by definition of GCD, D divides Rm and D divides Rn. Since M divides Mx and N divides Ny, imply from previous result we can write Rm will divide Rmx and Rn will divide Rny. Finding the results, D divides Rm and Rm divides Rmx, imply D divides Rmx. And second one, D divides Rn, Rn divides Rny, imply D divides Rny. So now writing again, D divides Rmx and D divides Rny, imply D divide their sum mx plus n, which imply D divides R1, imply D divide 1. So D being positive integer, the only possibility is D has to be 1. So hence GCD of Rm and Rn is 1. Answer.